Okay, I hope the screen is visible to all of you.
Yes, ma'am.
Okay, so in the last class, we discussed the basics of the transistors and also the working of a PNP transistor. So today we are going to continue our discussion on transistor and basically we'll begin with transistor characteristics, then we'll see a bit of uh, NPN transistor. So, okay. So let us start with transistor characteristics. In the diode characteristics, we have already seen that whenever we say characteristics, that means we are trying to plot something against some other thing. So if you apply the same logic over here, transistor characteristics are basically the plots that show the variations between input parameters and output parameters. So primarily when you talk about transistor characteristics, there are two main characteristics in a transistor. So these characteristics are, first of all, input characteristic, and the second one is output characteristic. These input characteristics are also sometimes known as emitter static characteristics. Emitter static characteristics. Whereas the output characteristic is also sometimes known as collector static characteristic. Okay. So now what the definition says, what is an input characteristic? It is actually a plot between input current and input voltage for different values of output voltage. Similarly, the output characteristic is a plot between output current and output voltage for different input currents. So why I wrote this entire thing over here is that, so this definition is very general. The definition of input characteristics is very general and output characteristics is also very general. Let us first see the input characteristics. So what do I mean when I say that this definition is general? That means irrespective of whether the transistor is a PNP transistor or it is an NPN transistor, or it is connected in a common base configuration, or it is connected in a common emitter configuration or common collector configuration, whatever it be, irrespective of all these factors, this definition will remain the same. But what is going to change is which current we are calling the input current, or which voltage we are calling the input voltage, or which voltage we are calling the output voltage. Likewise here, the output current, which current we are calling the output current, or likewise the output voltage and input current. So these, the value of these parameters or the designation of these parameters will vary depending upon if the configuration is common base, common emitter or common collector. So for example, in the last class, we took the example of a PNP transistor that was connected in a common base configuration. So if you get back to this circuit diagram and try to recall what we said. So we said that in this case, the input current is the emitter current. The output current is the collector current. And the input voltage in this case will be VEB. Likewise, the output voltage would be VBC. So here I write the input current in this case was emitter current IE. The input voltage is emitter to base voltage or the voltage across the first PN junction, and the output voltage is actually VBC or the voltage across the second PN junction. So if we now know these parameters and we try to plot the input characteristics in the active region, then this is how the characteristic is going to look like. So this is the characteristic for the transistor connected in common base configuration and working in the active region. So now looking at this characteristic or this plot over here, we are going to make a few observations. Okay? So the first observation is, we know that whenever a transistor is in active region, the emitter base junction is forward biased. And the other junction, that is the collector base junction, this is reverse biased. So because these are input characteristics, so we are not bothered about the second junction because this is the junction across which I usually take the output. So I am bothered only about this first junction. So given that this emitter base junction is forward biased, then the plot of current versus voltage is going to closely resemble that of a diode characteristic. So if you recall, in the diode characteristic also, the current versus voltage plot had this type of variation. So as you increase the voltage, until some time the current does not increase much, but once you exceed the cut-in voltage, then the current increases and the voltage drop across the junction nearly remains constant. So this transistor emitter base junction, when forward biased, is going to behave more or less like that of the diode characteristics in the forward bias region. So this is our first observation. Second observation is, I also want you to here mark that what are the variables mentioned on the y-axis and the x-axis. So since this is a common base configuration, so the input current will be the emitter current. That's why we have IE on the y-axis. The input voltage is the voltage across the first PN junction, that is VEB on the x-axis, and we will have different such plots over here for different values of VCB or VBC, that is the voltage across the second PN junction. So this was the second observation, that is you are marking the input current. Marking in the sense you are observing that what variables are present on the x-axis and the y-axis. Now coming to the third observation. So if I want to write an equation for this curve, how do I define this curve? Okay, I know that this is resembling the diode characteristics. I also know that this has been obtained experimentally, but if I want to write the equation, then how can I write the equation? So in order to write the equation, in case of transistors, you have the equation defined for the collector current. So collector current is given by IC is equal to IS into e raised to the power of VEB divided by VT minus 1. So this expression is almost the same as the expression for the forward current for a given diode. The only difference is here eta I am not writing, otherwise it was eta into V. So in this case, eta is equal to 1 if you are considering the silicon transistor. So that eta I have substituted 1, and then the collector current is given by this equation. And we also know the relation between the collector current and the emitter current. So we know that IC is equal to alpha times of IE, where alpha is the large signal current gain and its value is also close to unity. So I can say that the collector current is approximately same as the emitter current. So in this case, this curve which we are plotting over here, this can also be defined by using the same expression. So IE, this will be approximately same as IC, and this will be given as IS into e raised to the power of VEB divided by VT minus 1. Okay, so if I want to recreate these plots, I can change the values of VEB and correspondingly I can get the values of IE. So this was my third observation. Now,
what is
yeah.
IS? What is IS?
IS, so it's the reverse saturation current. It's the reverse saturation current across the junction. So you have other PN junction which is reverse biased, right?
Yes, ma'am.
So we are talking, ये जो equation है, this is not essentially defined for IE, this was defined for IC. And IC is at the second PN junction which actually is reverse biased. तो वहां पे दो करंट्स थे, एक तो रिवर्स सैचुरेशन करंट था और एक करंट था जो एमिटर से चल के आ रहा था, राइट? We saw this IC was equal to alpha times of IE plus ICO. So this ICO is this I reverse saturation current. That's why I just wrote this as IS. Okay. Okay. So now the fourth observation over here is about the cut-in voltage. So if you remember from our discussions on the diode characteristics, we say that initially the current value will be very low until you reach a cut-in voltage, which is defined by V gamma. And after V gamma, the forward current is going to increase. So for the case of silicon transistors, the value of this cut-in voltage is around 0.5 volts. So this is actually where I mark my V gamma or the cut-in voltage. So if at any junction the voltage is less than 0.5, say if I'm talking about the first junction, if this voltage is less than 0.5, or if I'm talking about the second junction, if this voltage is less than 0.5 volts, then for practical purposes, I can say that the junction is reverse biased. So this value you need to remember because this will be used in the numerical. So if it's a silicon transistor, then you need to remember that the cut-in voltage is 0.5 volts. Now what happens when the voltage across the junction exceeds 0.5 volts? Of course, it is no more reverse bias. Then we say that the junction is forward biased and we know that the current is going to increase in this manner. But while the current is increasing, what about the voltage drop at the junction? So in this case, the voltage drop across the junction VEB is assumed to be constant, that's equal to 0.7 volts. So here you see while the current is increasing, there is some voltage drop, but it does not exceed beyond certain value. So this entire region is actually approximated by considering that whenever this emitter based junction is forward biased, then the voltage drop across the junction will be 0.7 volts. So when we are solving the questions, this value will always remain fixed equal to 0.7 volts. Okay? Then, yeah.
How is alpha approximated to 1 here?
Alpha is approximated to 1 because alpha is equal to IC by IE. So the current which starts from the emitter, if you get back to this diagram over here, so the current that starts from the emitter, a very small portion of that current recombines with the minority carriers in the N region and create the base current, and rest all of it is transported into the collector region. So most of the current that starts from the emitter region reaches the collector region. That's why the fraction, what is alpha? Alpha is actually the fraction of emitter current which is reaching the collector current. So that is very, very high. Typically, it is around 0.98 to 0.99. That's why I have approximated this to be equal to 1.
So IB is negligible.
Yeah, IB is always negligible. Abhi, when we are going to see the characteristics, then you will see the difference in the units. when we mention IC and IE in terms of milliamperes, whereas IB is only in terms of microamperes, because first of all, the width of this base region is very small, and secondly, it is also lightly doped. So we do not have much conduction in this band, in this, base region. Okay.
Okay.
Okay. So coming back to this plot, so the fifth thing that I wanted to mention was, so here in the equation, you see that IC is actually not dependent upon the output voltage VCB. So if I write this equation over here, you see that we do not have the term of VCB, where VCB was what? It is also the output voltage, as well as it was also the voltage drop across the second PN junction. तो why IC is not equal to VCB? यहाँ पे क्यों नहीं term आ रहा है? Because this voltage is actually the voltage drop across the second PN junction. If I increase the value of VCB, then what happens is I only increase the reverse saturation current. And from this equation, I know that reverse saturation current is a very small component of this collector current. So even if this increases by some value, this is not going to make much difference to this IC. That's why whenever we write the equation for IC, we do not consider VCB, and we say that for all practical purposes, the collector current is independent of the output voltage or the voltage drop across the second PN junction. So this is for practical purposes. But theoretically, we see that there is some dependency of IC on VCB. So how can I explain that dependency? So for example, I'm increasing VCB. So we know that VCB is the voltage drop across the second PN junction. And since my transistor is in active region, so the second PN junction is reverse biased. That means increasing VCB is actually increasing the reverse biasing across the second PN junction. अगर reverse bias increase होगा तो क्या होगा? This is going to widen the depletion layer. If the depletion layer widens, that means the base width further reduces. Base width is going to reduce further. Already the base was the narrowest of all the three layers, but if you increase the reverse bias across the second junction, the base width further reduces. So now if the base width reduces, then what happens is that between emitter to base, the concentration gradient increases. The concentration gradient increases. Why it will increase? Because already the base was lightly doped. Now that you are further reducing the width of the base, then there are very less carriers in this region. So in this emitter region, you have large number of holes, but in the base region, you have very few holes that too have been reduced because of the reduction in the base width. So this increase in concentration gradient actually increases the emitter current. And when emitter current increases, the collector current also increases. So although the increase is not very significant, and for practical purposes for solving the questions, this dependence can be ignored, but theoretically we need to keep in our mind somewhere that yes, this has some slightest dependency on the output voltage VCB as well. So this you can observe over here. So here you have two plots. In the first case, VCB is shown as 0. And in the second plot, VCB is shown as -10. That means what you are doing, you are actually increasing the reverse bias. So if you increase the reverse bias, then for a given value of VEB, the current increases. So for example, let me take this middle point. This middle point is how much? Say this is 0.65 volts. So if I take this 0.65 volts, then when VCB was 0, then the emitter current is something. And when VCB is increased, I mean, if the reverse bias is increased, the emitter current slightly increases over here. So this will be delta IE. Right? So this observation says that although the dependence of IC with VCB does not occur in the equation, but theoretically there will be a slight increase if you increase the reverse bias voltage across the second junction. And the last thing is, over here you have one more plot which says that this is open circuit. Open circuit से यहाँ पे मतलब है कि you have not connected the collector terminal, that is IC is equal to 0. So if you have not connected the terminal, there is no role of the other PN junction. So it behaves as if the circuit only has one PN junction and which is forward biased. So this plot will be exactly same as the plot that you saw while drawing the diode characteristics. So from the input characteristics, these are our observations. To summarize, the first observation is about writing the equation for this emitter current, which is in turn derived from the equation of the collector current. Second observation is about the variables that are appearing on the X and Y axis. Third observation is about the cut-in voltage. So the cut-in voltage will be assumed as 0.5, whereas if the diode is forward biased, VEB can be fixed as 0.7 volts. Then we talked about the dependence of IC on VCB. So theoretically, there will exist some dependence. And the last thing is about the open circuit condition. In this case, this plot is going to resemble exactly that of the diode characteristics. So this was the plot between IC and VEB. So if someone says that we need to show a plot between IC versus VEB, then that plot is also going to look exactly the same. Why? Because we know that IE is approximately same as IC. So that plot can also be shown. Any issues as of now? No? Okay, so if there are no issues in this, let us discuss briefly about the output characteristics. So again, these are the output characteristics for the transistor connected in the common base configuration. So while we were defining the output characteristics, what we said that output characteristic is the plot between output current versus output voltage for different values of input current. So if it's a common base configuration, what is the output current? Output current is the collector current IC. Output voltage is VBC and the input current is IE. So the first observation we make over here is to cross-check the variables. On the y-axis, we have IC. On the x-axis, we have VBC. And then this plot is repeated for different values of emitter current. Now, based on this output characteristics, we can actually differentiate the region of working of this transistor. How we can do that? So for this, first of all, I would like you to come to this last line where it's written that IE is equal to 0 milliamperes. So if IE is equal to 0 milliamperes, that means the emitter is open. Or we can also say that in this region, the emitter base junction is reverse biased. Because if any junction is forward biased, then through it positive current is going to flow. This we know. So if anywhere the current is 0, that means the junction is not functional. We say that it's reverse biased junction. So first junction is reverse biased is what we conclude from here. Now how about the second junction? So for second junction, we need to check on the voltage of the second junction. That is, we need to check what is the status of VCB. So earlier in the earlier slide, we said that if VCB is less than 0.5 volts, that means the voltage drop across it would be less than the cut-in voltage, and then we can say that the junction is reverse biased. So here instead of VCB, we are actually plotting VBC. So if you reverse this, this will be how much? This condition would translate to VBC greater than minus 0.5 volts. So here minus 0.5 is marked, and this region where you have VBC greater than minus 0.5 volts that means the region where the second junction, that is VBC or the collector base junction, is also reverse biased. So in this region, this is also reverse bias, this is also reverse bias. Therefore, we call this region as the cutoff region because both the PN junctions are reverse biased over here. Then the next thing is, when the junctions are reverse biased, at that time we know that only the reverse saturation current flows. So across the first junction, reverse saturation current is not going to flow because the emitter is not connected. The emitter is open. So the reverse bias current flows across the second junction, and we give this current the name ICBO. So here it's minus because it's denoting that this is a reverse saturation current. And what do these initials CBO refer to? So this means that the reverse saturation current, which is flowing from collector to base by keeping emitter as open. So this, because it's a reverse saturation current, its value is very, very small. So this value is on the order of nanoamperes. Whereas if you see the plot that we are showing here, the collector current is on the order of milliamperes. So that's why you do not see any region over here, and it looks like this IE is equal to 0 line is almost same as the horizontal axis, but actually it is not. If you zoom in and zoom into, you know, whatever possible, whatever projection is possible, then in that case you will observe that there is slight difference between the x-axis and the line IE is equal to 0. So the summary over here is, in the cutoff region, IE is 0. The condition is that VBC is greater than minus 0.5 volts, and during this time only one current is going to flow through the transistor, that is ICBO, and its value, since is very small, this line is going to appear as if it's coincident with the x-axis. So this is our first observation. Then what happens if I increase the value of IE? Now see over these lines. So here IE is 2 milliamperes, here 4, here 6, here 8. So for all these regions, we say that now IE is greater than 0. That means the emitter base junction now becomes forward bias. So here emitter base junction is forward bias, but still we are talking about this region where VBC is greater than minus 0.5. That means although this junction is forward bias, the collector base junction is still reverse bias. So that means to the right side of this dotted line, we can show that the transistor is operating in the active region. And when the transistor is operating in the active region, two things I would like you to verify from here. The first thing that we read in the last slide was that IC should be approximately same as IE. That's what we can confirm from here. So here IE is 8 milliamperes, correspondingly IC value is also 8. Here this is 6, correspondingly IC is also 6. So it's not that we have drawn like this and labeled like this. When you experimentally do the things and based on the observations you plot the graph, then you will see that for this value of IC, IE, you will get this value of IC and vice versa. So this is how we confirm that yes, in the active region, IC is approximately same as IE. And the second observation that I would like you to validate over here is that we just said that IC for all practical purposes is independent of the output voltage VBC. So that's what is happening. As I'm increasing VBC over here, the IC plot is almost constant. These values are almost flat. So although theoretically it may make little difference to IC or IE, but essentially this is going to remain constant as long as the transistor is operating in the active region. And then what about the saturation region? So if you move towards the left side of this minus 0.5, that means now we know that this condition is being violated. So over here, the collector base junction also becomes forward biased. And as long as the current IE is greater than 0, that means along these plots, we have the emitter base junction also forward biased. So when both the junctions are forward biased, we say that the transistor is operating in the saturation region. So across both the junctions, we will have forward current. So collectively, it will appear as if the current is increasing exponentially in this region. And this exponential increase will kind of saturate as you reach this minus 0.5, where the second junction kind of goes into reverse bias. So based on the output characteristics, we can differentiate the region in which the transistor can be operated. Any doubts? No doubts? Okay. So if there are no doubts, then we will see a small question to have some confidence, and then we will start the discussion of the NPN transistor. So here in the figure, it has been given that RC is some value, RE is also given, and VEE is also given. Alpha is given, we need to take its value equal to 1. So what is required to find? It's required to find VCB when VCC is 12 and the minimum value of VCC such that the transistor is in the active region. So now how does the analysis differ with respect to the analysis that we have done earlier? If this is the question, then I'll say that the analysis will not differ, just that there is slight difference in the settings. So what is that? So initially we have been using KVL and KCL. So here also we are going to use KVL and KCL. And how you are going to apply is that if you look over here in this circuit diagram. Okay, one more thing. Before we start the analysis, I would like you to observe the direction of the current that is marked. So keep in mind, this is the PNP transistor. And for a PNP transistor, the direction of the emitter current, the collector current, and the base current is always going to be marked in this manner. This is very important because if for a PNP transistor, you reverse the direction of currents, you may get different answers. So therefore, whenever it's a PNP transistor, your emitter current will be inwards, base current will be downwards, and the collector current will be outwards. Whereas if you talk about an NPN transistor, in this way, then when we study the NPN transistor, tab to wahan pe dekhoge, but here also I want to briefly mention that for an NPN transistor, the direction of current is IB goes inwards, IE goes outwards, and IC goes inwards. Why this happens, we'll talk. Yeah.
If the CV is reverse, collector base junction is reverse biased, then shouldn't IC be into the junction?
No, IC will not be into the junction because
no, if it is
IC
forward biased.
What, this junction?
Yes, ma'am. Collector base junction.
Okay, so that we will talk later when we will discuss about the transistors working in saturation. Okay, where both the junctions are forward biased. So ye direction of current ki tab baat karenge. Just do not confuse right now. We are talking about the operation of the transistors in active region. Okay, I'll get back to this point when we discuss it over there. So for now, you remember that the direction of the currents, if it's a PNP transistor, will always be like this. Do not do any mistakes in this. Okay, so once we have this, we also see that this is a PNP transistor and it is connected such that base is common between the input terminal and the output terminal. So now what we see over here is that there are two loops. So one loop is this and one loop is this. So generally in the transistor, we have two loops. One is the emitter base loop and the other is the collector base loop. So what we are going to do is, to solve our purpose, we are going to apply KVL to each of these loops. So let us begin with the first loop, that is the emitter base loop. So what happens over here? The process is same. Say if I start from this point, my KVL equation will be minus VEE plus IE RE plus the voltage drop across this junction. So voltage drop across this junction is VEB. And this should be equal to 0. So what is unknown and what is known over here? VEE is already given. This is minus 1.4. IE is something that I don't know. RE is given as 180. And what about VEB? VEB is not given in the question, but we know that VEB will always be equal to 0.7 volts because the emitter base junction is forward biased. So now we have only one variable, that is IE, and we can calculate its value as say 1.4 minus 0.7 divided by 180. If you calculate this, this comes out to be 8.39 milliamperes. So I have my IE from here. Now the question asks us to find out VCB, and we know that VCB is the part of other loop, that is the collector base loop. So what we do now, we'll apply KVL again to this loop. So इस loop में KVL apply करोगे तो what are the voltage drops? You have minus VCC minus of VCB plus RC IC is equal to 0. So here if you see, the polarity is marked plus over here and minus over here. If you want to take it the other way around, that is plus over here and minus over here, then you need to change this notation. Then in that case, we will not say that this is VCB, rather we will say that this is VBC. And VCB is actually equal to minus of VBC. So be careful while you are marking the polarities or naming the voltages. Here I am taking the convention which is shown in the question itself. So that's why I said, because I'm starting from here, so this is minus VCC, then minus VCB plus whatever is the voltage drop over here. So now what is the unknown? What is the known? VCC is given because we need to calculate the parameter at 12. So we'll say that this is equal to minus 12. This is not known. This is actually what I have to find out. Plus RC is given. This is 1.8K and IC. So IC is not given in the question, but I have just found IE. And I know that if the transistor is in the active region and it's connected in a common base configuration, then IC would be same as IE. So what I do is I substitute this 8.39 milliamperes over here, and this is equal to 0. So if you solve this equation, you will get VCB is equal to minus 5 volts. Is it clear how do you apply KVL to this base emitter and collector and base loops? This is very important to understand because again and again you will be doing the very same thing. You will identify the loops, apply KVL in the loops, and then solve for the answers. What are the voltage drop? One voltage drop is across this junction, other is across this resistance, and other is the voltage that's applied over here. Similarly, in this loop, one is the voltage drop across the junction, one is the voltage drop across this resistance, and then this voltage is applied over here. So if this thing you understand, then you can solve these questions like before. Okay, so this was the first part. Then what about the second part? Second part says that find minimum value of VCC such that the transistor is in the active region. So for the active region operation, I know if the transistor has to operate in active region, then IE should be greater than 0 and VCB must be less than 0.5 volts. So what I'm going to do is I'm going to use this condition. So yahan se this equation you have already written where you have VCB in terms of VCC and ICRC. So what I'm going to do is I'm going to rearrange this. From here I can say that VCB is equal to minus of VCC plus ICRC. And this.
How did we get that VCB is less than 0.5 volt?
This is the condition. This is the condition because 0.5 volt is the cut-in voltage of a PN junction if it's a silicon transistor. Okay, so if I want any junction to be reverse biased, then this value you should remember that the junction voltage should be less than the cut-in voltage. And the cut-in voltage value is 0.5 volts. ठीक है, अभी देखा था ना यहाँ पे यहाँ पे देखा था ये कट इन वोल्टेज मार्क किया था, दिस इज द सेम 0.5 volts.
Yes, ma'am.
ठीक है. So this VCB should be less than 0.5 volts. That means this equation you rearrange minus VCC plus ICRC is less than 0.5 volts. So IC you know, IC निकाला था यहाँ पे 3.8. RC also you know, RC is given in the question. This is 1.8 kilo ohms. So you just have to find out the value of VCC. I'm giving you the answer here. After the class, you try to cross check the answer. So the answer to B part is VCC should be greater than 6.5 volts. This is the answer to B part and this is the answer to A part. इसको एक बार करके देखना. ठीक है, any doubts? No doubts? Okay, then I'll start with the NPN transistor. So working of the NPN transistor, I'm not doing again. In the book also, it's not discussed again because the working is essentially same. The only difference is that the majority charge carriers in case of PNP transistor was holes and the majority charge carriers in case of NPN transistor is electrons. So wherever they talk about the majority charge carriers, you have to think of electrons in place of holes while discussing the working of the PNP and NPN transistor. Other than that, all the concepts that we have seen remain the same. So set this, in this example, we are going to discuss the common emitter configuration. एक transistor common base में देखा, now we'll see another transistor in the common emitter configuration. So you see the way this transistor is connected. This is tilted such that the emitter terminal is common to the input as well as to the output. So that's why we say that this configuration is the common emitter configuration. Then again, here I am talking about the operation of this transistor in active region. And whenever the transistor is operating in active region, I know that the emitter base junction has to be forward biased and the collector base junction has to be reverse biased. Acha, yahan pe now I will not say EB junction, I will say BE junction. Likewise, I will not say this CB junction, I will say this as BC junction. Kyun? Because B is the P type and C is the N type. Earlier, C was the P type, B was the N type. So जब कहते हैं तो we say that this is a PN junction, right? We don't say that this is an NP junction. Although the working will not change, but for the sake of convention, we say that PN, it's a PN junction. So जब लिखेंगे तो we will write such that the terminal, which is P, is written first. So here what we need that the BE junction is forward biased and the BC junction is reverse biased. So in this configuration, if you look at the circuit diagram, how can I have the BE junction forward biased? This is simple. This is simple because we have a power supply attached to it. So if I increase the value of VBB and it is large enough, that is more than the cut-in voltage, then obviously I'll be able to forward bias this VBE junction. Then what about the other junction? So for the other junction, I know that if the other junction has to be reverse biased, then the voltage drop across the second junction, that is VBC, this should be less than the cut-in voltage V gamma, whose value is 0.5. This we already saw from the input characteristics that whenever the potential drop across the junction is less than the cut-in voltage, then for practical purpose, we can say that the junction is reverse biased. So this condition is actually in terms of VBC, but in this configuration, when you say that the emitter is common, VBC is kind of internal voltage. VBC is kind of internal voltage which may not be easily accessible from outside. So what I want to do is I want to translate this condition in terms of output voltage VCE. So here if you see, the output voltage is taken across C and E terminals. So in this case VCE is supposed to be the output voltage. तो यही काम पिछले वाले केस में क्यों नहीं किया था? We did not do this for the last case because over there the junction voltage and the output voltage was the same. If you recall, over here the output is taken across collector and base, and the junction voltage is also across collector and base. So the condition on the junction voltage was also a valid condition in terms of output voltage, right? Or if you say that my output voltage is VBC, then you can simply say that if VCB is less than 0.5, VBC will be greater than minus of 0.5. That was one straightforward way. But here we need to do some readjustments so that we can translate this condition of junction voltage in terms of output voltage. So how can I do this? So for this, I want you to get back to this symbol. So across this symbol, you see that there are 3 voltages drop. And by KVL, the voltage drop sum net should be equal to 0. So if I apply KVL over here, the condition becomes minus VBE plus VBC plus VCE is equal to 0. That means VBC will be equal to VBE minus of VCE. And this voltage VBC must be less than the cut-in voltage V gamma for this junction to be reverse biased. Right? That means VBE value I know, this will remain constant. This will be equal to 0.7 volt. VCE पे तो मुझे condition ही चाहिए, and the cut-in voltage also I know, this is equal to 0.5 volts. So if you do the rearrangement, this condition translates to the fact that as long as VCE is greater than 0.2 volts, the second junction is going to be reverse biased. Right? So in this case, whenever you see a question where you have a common emitter configuration and it's asked find blah 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 parameters, given that the transistor is in active mode, then for reverse biasing of the second PN junction, we are going to use this condition instead of this condition. Although both the conditions are same, but believe me, applying this condition is much more easier because VCE is the output voltage. So the conditions over here is, first of all, input current has to be greater than 0. So IB has to be greater than 0. This means that we have forward biased the base emitter junction. And the second condition is VCE should be greater than 0.2 volts. That means here we have reverse biased the base collector junction. So these conditions you need to remember, and they will hold true if the transistor is in the active mode in a common emitter configuration. Okay? One more thing I'll quickly take before we close is this output characteristics, because all the concepts are same, only the difference is in the variables. So because this is the output characteristics, we know that this will be a relation between output current and output voltage for different values of input current. And since this is a common emitter configuration, the output current is of course IC. The output voltage, this is VCE in this case, and the input current is IB. So one thing that I want you to observe is here you see IC is in milliamperes, whereas IB is in microamperes. So that's why we say that the base current is very, very small compared to the emitter current or the collector current. Then we can again identify the regions just as we did in the previous case. So if you come to the last line here, they say that the input current is exactly equal to 0. So if the input current is 0, that means the first junction is reverse biased And also the reverse biasing condition on the second junction is that VCE should be greater than 0.2. So 0.2 is marked over here. So for all the voltages greater than 0.2, the second junction is also reverse biased. So we say that in this region, the transistor is in cutoff. A small reverse saturation current will flow that we call as ICEO. So CEO denotes, E here denotes that this is for the case when you have the common emitter configuration. So this basically means the current which is flowing from collector to emitter with base as open. So this is what it means, but basically it is a very small reverse saturation current which is flowing through the second junction. Then how about the active region? So in the active region, we say that the input current value has increased from 0 to greater than 0. So for all these regions, IB is greater than 0. But since we are still in this zone and we have VCE greater than 0.2, so this is the active region. And to this side over here, so if VCE is greater than 0 is the condition for reverse bias. That means if VCE is less than 0.2, the junction will be forward biased. So in this region, when the value of input current is greater than 0, that means corresponding to all these curves, the transistor is going to operate in the saturation region, wherein both the junctions will be forward biased and collectively the current will look like as if it is exponentially increasing. So this was one observation. And one last thing over here is that the curves that you see over here, तो पहले वाले case में क्या था कि this curve was almost flat. And we said that in that case, IC was independent of, IC over here was independent of the voltage VBC. So this was almost flat. But when you talk about the transistor which is connected in a common emitter configuration, then the variable on the x-axis changes if you are plotting the output characteristics. So now this is VCE. So these curves will not be as flat as we saw last time, but there will be some slight slope over here. इस diagram में तो इतना apparent नहीं है because the book does not give much clarity. But if you refer to other books which are more standard books, there you will see that for the case of common emitter output characteristics, the plots will not be so flat. It will be kind of having some slope. So that means IC is going to increase as you increase the output voltage. And this is true also. If you look over here, so what is VCE? VCE is actually same as the voltage drop in this parallel branch. So here this may be fixed, but then the voltage drop across this is dependent on RC value. So that's why the plot will not be a very flat line that you observed in the previous one, but it will have some slight increasing slope. So this was all about the NPN output characteristics. Next time, we'll talk about a few more parameters and maybe try to solve one or two questions based on this common emitter configuration. If there are any doubts, you can ask now. Otherwise, I'll close the meet. No doubts? Okay.